Okay, welcome to your second lecture for Eng 1500. This is one of my favorite lectures to give in the entire course. I absolutely love this lecture. It's broken up into a couple of different parts, and whilst I'm going to record all of these in one take, you may want to consume it in a couple of different sections. And there'll be some good reasons for that you will see as we go through. It'll be littered with blue slides and black slides to tell you when good times to take breaks and stuff like that are. But I'm also going to start with sort of 10-ish minutes of admin stuff that it's really quite important that everybody is on the same page with this. So bear with me for 10 minutes and then we'll have some cool lecture content to go through. So the first thing I did mention I was going to start doing this is there is a worksheet to go with this lecture. It's a series of questions that I want you to do them because by having a think about these questions before we start, it will make consuming this lecture content significantly easier for you. So it is up. There is a link to it below there where it's on Blackboard. It is also going to be I'll email you a link to this video and I'll put the worksheet in that as well. All right, so spend 15, 20 minutes on it. Don't spend ages. You don't need to get a perfect answer to every question. It's just to get your brain cells ticking over first, okay? There is also going to be some discipline-specific videos to go with this. I'm going to do an example through the spine of the models and assumptions part of this lecture, and it's an example from one particular field. There is then, correspondingly, a whole bunch of other videos for you to watch related to your discipline. Okay, so when you get to the end of models and assumptions, go and watch your discipline-specific video, or when you get to the end of this lecture. Regardless, watch it before your workshop because your workshop leaders are assuming you have seen it, all right? And they have often built content based on that. Some of your workshop leaders, so much so, needed this to integrate that they made that video themselves and they are assuming you have consumed it as part of the lecture, okay? Also, I made some of these videos at this time last year and they were pre-COVID. It's kind of funny you get to see the old way I got to make videos. Interesting. Okay, just to clarify a few things for you about the fact that some things are supposed to be unclear for you. At the moment, it may seem that Eng 1500 is a little bit chaotic, and it is meant to be a little bit chaotic at the moment. It's actually quite intentional that some parts of this are unscoped. They are meant to be. And I have very good reasons for this. I'm going to take you through what your first 6 weeks of lecture content are going to look like, and then we're going to talk a little bit about how that relates to your project and the order for you to do things in. So, your first 6 weeks are super content heavy. I'm going to smash you with lecture content right up front. It's called front loading for obvious reasons. And then we're going to start to really ease off. And we'll still give you content week to week in some or most weeks at the back end, but it's very complementary content. So big heavy hits of content. Week 1 was all of the intro stuff so we could start. Today, models and assumptions, research and units, fairly big content dump. Next week will be the engineering method. So it is a systematic way of solving problems, particularly open-ended complex problems like the ones that you all have, all right? So you don't just want to charge headlong into solving your problem. That's a really, really dumb thing to do. Don't start yet. Wait till you get the lecture that teaches you how to do it. You're also going to get a week 4 lecture where we're going to start our communications journey. How do engineers communicate, which happens in 3 parts. Part in week 4, part in week 6, part in week 8 or 9, depending on how we're going. And week 5 is design thinking, along with a bunch of other stuff like teamwork, skills and dynamics, and assessments and how they're laid out. So that's super important before you can really do a whole heap of committing to your project as well. All right, so you really want to get that content. Week 6 will be engineering report writing, but you really want to get the week 5 and the week 3 content before you try and solve your problem. It's why, to some extent, I'd almost prefer to not even let you see your project descriptions for the first 5 or 6 weeks. But obviously you need to see your project description so you can kind of get where you're heading. But we don't want you to start solving your problems now. The main reason being a thing called first choice fixation, and it is deadly. You get an idea in your head and you generally form it based on uninformed opinions. Not the greatest sentence I've ever concocted in my life, but you get a first idea And then you start to evaluate every other idea in comparison to that. Whether that is conscious or subconscious, you do. It's just how the human brain works. And that can lock you into a particular way of thinking, which can be really, really problematic for making good progress. Okay? And we don't want you to do that. And that's why we leave you in the dark on certain things. We're trying to stop you committing to an idea. Okay? But there you go. You get a little bit of the map of 1500. Couple of housekeeping things to smash through, and then we'll get into the cool lecture content. The ES126 induction quiz is still broken. You can see it, but you can't see any content. I don't know why. I don't think I can fix it. I'm going to put a bullet in it, and I'm going to rebuild it from scratch, and I'm going to give you something new next week. I'm just giving up. I'm trying to fix... That was first choice fixation. I was trying to fix something that was broken when I should have just scrapped it, put it in the bin, started again, so that's what I'm doing. So yeah, if you've got an ES126 induction to do, it'll take me a while to get it set up. Don't stress. If you're doing the EE inductions or the RB workshop inductions, they are both up. You can both do them. Heaps of people have already done them. Well done to anybody who's already finished. Can everybody else please do them? We will make you show us in week 2 or 3. Probably 3. In terms of contact with me, my interaction with you, Discord's been going great. That's been fantastic. I've had loads of conversations already. It's really great to see everybody on it, and it's really great to see you interacting with each other and helping each other out. There is a new channel that's been added for STM help. So if you're having problems with your STMs, chuck it in there, and hopefully, because I know all of you are having the same problems, you can help each other out. The invite is now closed, and this is for security reasons. I don't leave my Discord open forever. So it was open for a window. That window is now over. It is now locked. So I can send you a new invite, but I want to kind of understand why at this stage, because if you're not in, is that because you missed your week 1 workshop? That means you're not in a team. That means we've got bigger problems, all right? So email me if you need to get back into the Discord, but it's now closed. Make sure your nicknames are the same as the names on Blackboard. I'm going through tomorrow, so make sure they're right. That's first name and last name as it appears on Blackboard, okay? And you can the video that I sent you on how to use Discord teaches you how to do it. It's really not hard. It only changes your nickname in that server, so you're perfectly fine for your username to be whatever it is, as long as it's not offensive. It can be whatever it wants to be. Just your nickname in the server needs to be correct. And please, my most common email is still what degree are you doing or what project are you doing. So whenever you're emailing me, include your degree within your thing. All right. Also, the live stream was awesome. There was really, really great engagement from you all. Thank you for bearing with me through me posting the wrong link twice and then dropping. I promise I'll do better on Tuesday. But thank you to everybody. It was really good. They were really good questions. I'm sorry. I know I rewatched it and I realized I missed so many questions. I just could not keep up. So please come back. Keep asking questions. It was really, really good. Awesome. Your assessment task. Remember, this is your first assessment task. It's a quiz. It's on Blackboard. It is up. Only half of you have done it. What are you doing? It's the cheapest 5% you'll ever get at university. If you haven't done it yet, please log in. Please do it. Just so you know, it will auto-submit after 60 minutes. This is because if you don't hit submit or you hit submit and it doesn't work, I can't mark it. It's a thing with Blackboard. So it'll auto-submit after 60 minutes. If you're not finished, just redo it. Okay? Redo it as many times as you like. If you don't have 21 out of 21, redo the quiz. It'll disappear next Monday, which I think is the 8th. Okay? And after that, you've got the grade that you've got in there. You had 2 weeks to do a quiz that takes 30 minutes. Get it done. It asks you to print a test page. I got a bunch of questions in the live stream about this. I don't know how well I explained it, so I'll just reiterate it here. It asks you to print a test page at university using your print credit. It can be any page you want. I don't care. You don't actually have to print the quiz. You write your name into a Word doc and hit print. It's because loads of people have errors the first time they do that. And if you have to print an assignment at uni, you don't have to. You can print all your assignments at home. That's fine. But say you rock up and you realize, I don't know, you're missing a page because you left it on the printer at home and you want to print it at uni and you can't because you need IT to fix your printing account. You don't want to realize that half an hour before your assignments are due, so please print a random test page. You don't have to show it to me. You don't have to submit a hard copy of the quiz. You will have to submit a hard copy of your first report. Just so you know, a bunch of those questions in the quiz, I'll ask you them again in week 13, and we'll get to compare your answers from then to now, and we'll see how they compare. It's a really cool learning exercise. Also, 16 of you haven't gotten onto Blackboard yet, and I'm a little bit worried about you, so you may get an email from me. Please log on to Blackboard if you haven't yet. I know there's not a whole heap to do other than, you know, an assessment task, but just log on for me. Cool. Awesome. Admin out of the way. It took almost bang on 10 seconds. I'm stoked about that. Let's get into the first part of this lecture, assumptions and models. I know some of you have heard a little bit about this in your workshops already, but let's do it in proper detail. All right, so as an engineer, when I say models, what do I mean? No. No. Also no. Also no. When I say models, I mean mathematical models in general. Sometimes, yes, engineers will build these scale models, prototypes, scaled models. This is a thing that we will do generally to validate a mathematical model that we already have. Okay, so most of what we do as engineers is we look at the universe as it exists and we make models of it so that we can solve parts of it with maths. Okay, so this is the example that I've given you, and look at the worksheet if you haven't looked at the worksheet, but if you haven't, how far can you, or can I, throw a ball? What do you reckon? If I was to walk outside and hoik this sucker as hard as I can, how far do you reckon it would go before it hit the ground? Follow-up question. Can you calculate that? And further follow-up question, can we then predict something, or can I throw at a particular velocity that you tell me to make it land somewhere specific? So let's give this some engineering context. It's not Dylan hoiking a cricket ball as far as he can. We're going to build a robot that shoots free throws. Now, I understand this is going to be a thing that not all of you are necessarily going to see why this has immediate relevance to your project. That's fine. Remember, there are discipline-specific videos to go with this. So, what mathematical models would we be using to calculate the trajectory of this basketball and whether it would go through the hoop? I'm sure many of you have seen this already, and if you haven't, it is the projectile motion model. Okay, so this is quite a common model for people to see in high school or sort of first year university, and I'm sure you will see this in maths or physics or somewhere in the near future if you haven't before. Don't stress about the maths in here if this is a little confronting to you. You don't actually need to understand the maths to understand what I'm going to talk about today. But this is a real world scenario that we have a mathematical model for. Okay? The projectile motion model allows us to model the flight of an object. Cool. It relies on two primary things. Having a set of initial conditions. So this is an initial velocity. How fast was the thing moving when you threw it? And at what angle? And at what position? Where did you start? So initial conditions. And it relies on there's an acceleration due to gravity for things to go up and, you know, come back down. Otherwise, they would just float forever. But they're the two things on which our model is based. So knowing that, what we can do is apply a few more modeling steps. So we can take Newton's laws of motion, force equals mass times acceleration, F equals ma. It's more strictly correct to say the sum of all of the forces on an object equal the mass times the acceleration in either the x direction or the y direction. Same math, you just split it up. So we do that modeling step, and then we apply maths to it. Now, this is integration. So we take an acceleration, we integrate it to get a velocity. So the velocity is the integral of acceleration. Again, if you haven't seen this math, don't worry about it. The point of my story is you get acceleration, you apply maths, you get velocity, you apply more maths, and you get displacement. S means displacement, by the way, for reasons. You can do this in the x direction. You can do the same thing in the y direction. It's a bit of a different equation because of gravity. But you get these two equations that tell you about how the thing moves. And if you've got that model, you can put in different conditions and you can work out things like how far the thing goes, what its maximum height it reaches is, all sorts of jazz, okay? So it's like range and max height and all that kind of stuff is easily calculated from the model from that point. So hopefully you can figure out that purple dot being our basket, with what initial conditions can we make sure our basketball intersects the area that is the basket, and we can score a basket. Congratulations. So we have all of that, we put it all together, we have our projectile motion. Really commonly taught thing. And the one thing that I can say with absolute certainty about this model is that it is wrong. Any calculation you've ever done with it is wrong. It is not where the basketball would go. Wrong. And I know this because all models of our universe that we use in engineering and science are wrong. Which may sound disheartening, but don't worry, we're going to cover why it's not such a big problem. The main reason they are wrong is because they are based on a series of assumptions about the real world, okay? So this was another thing that hopefully was in your worksheet. Can you think of any reasons why this particular model may not exactly add up with the way the world actually is, with where the real world basketball actually goes? If you haven't done the worksheet, please pause here, think about it for a little while. What are some of the reasons there will be discrepancies? And there are quite a few reasons. We're going to go through some, but yeah. What can you think of? So here's the ones that I could think of. Here are some of the assumptions that we make when we do the projectile motion calculation. First, and the one that almost everybody gets, is it doesn't compensate for drag. There is no aerodynamic drag in the normal, or at least in the projectile motion model that I just showed you. There's no drag, which means the drag on the sphere, the drag on the basketball, isn't calculated for. So you probably have to throw it a little harder than you calculated, or it would be slightly wrong in the prediction of where it's going to end up. So that one's pretty obvious. There are, however, quite a few more. What's gravity equal? You may remember in the maths we went some of the forces in the y, and we had a gravity term in there. It was just called g. What's g? Is it 10? If you do engineering studies in high school, you generally just use 10. Most people will get up on their high horse and tell you, no, it's 9.81, which is also wrong. In Australia, nowhere is the gravity, except maybe at the very tip of Tasmania, equal to 9.81. In fact, it's generally closer to 9.80, and to be more accurate, around Newcastle, 9.9795. Not 9.81, 9.80. Also, as you can probably tell from that map, it is not constant. It changes based on where you are on the Earth. It also changes based on your altitude. Cool. Okay. So we don't even know what gravity is. Also, we don't know whether the Earth is flat. The projectile motion assumption assumes the Earth is flat. Okay? It does not compensate for the curvature of the Earth. The Earth is not flat. But we assumed that it was in our model. We also made a 2D assumption. Get the cricket nerd out in me here. We assumed two-dimensional, right? Okay, so there was only one direction it was traveling. But if anybody's ever known how to swing a cricket ball before, this is a new cricket ball and this is an old cricket ball. It gets a shiny side. You can end up, if you work on it correctly, to get a shiny side and a rough side, which changes the way that the drag is distributed on the ball, which makes it move sideways. Which means the range you calculate, because it's not just moving in one direction anymore, it's moving a bit sideways, will be different. You'll miss. This is subtle often with a cricket ball. It's real obvious with a boomerang. In fact, your range, when you throw one of these boomerangs, generally your goal is to make your range be 0, right? Make it go all the way around and come back to you. So depending on your projectile, this could be a massive assumption that may not be true. Probably something that is fairly true, but is still an assumption, is the classical physics assumption. So we use Newton's laws, sum of the forces equals ma. Einstein come and proved that, and some other people obviously helped, it wasn't just him, but looked into this and basically determined that, well, no, any object is actually subject to relativity. This piece of special relativity, whether we're talking time, mass, or space dilation, the faster we're going to the speed of light, we start to experience dilation, time-space dilation. And due to this, our model is to some extent wrong. It doesn't compensate for special relativity. We're also quite sensitive to our measurement and initial conditions. So you will see these questions asked quite often in a math textbook, and it will say, at an angle of 42 degrees and a speed of 5 meters a second. Which is fine, but how did you measure that? Because the only real ways to measure speed, velocity, are to take a distance traveled over a time, and then you get an average. But we know we have drag, so we know our projectile is slowing down as it moves, so we're not really getting our initial conditions, we're getting some average. So there's always measurement error. Sometimes it's really small, sometimes it's massively big. Cool. And there are more. This is some. I really like to do this live because people always shout out things that I've never even thought of, and it's a really cool thing to do with 700 people in a room, so I'm sorry you get to miss that. But this is a small subset of the assumptions that we will be making. And for all of those reasons, our model calculates something incorrectly. And so we have an error on our model. Why do we teach it? Well, just because a model is wrong does not mean it is not useful. If it wasn't useful, we would probably not teach it to people. Probably not. So, it's wrong, but it's useful. Your job as an engineer is to solve problems. It's to build a robot that can shoot baskets. Now, the fact that some of your models are slightly wrong doesn't mean you care. Your job was to shoot a hoop, right? You didn't calculate for relativity. You are wrong by a few nanometers as a result, probably less than a few nanometers. You're wrong. You don't care. Don't care. It's not worth solving for that, all right? So you need to have a good understanding here of what you are actually doing and what are you trying to achieve. And then that will help you understand how useful these models can be to you. Okay. The fewer assumptions, meaning not as many, fewer, the less, meaning smaller or better our assumptions, the more accurate our model is. So we could add the relativity component into our model, and then it would be a better model, and we would be more accurate, right? But that is a lot more work. So you may not want to go to all of that extra work to get that small increase in accuracy. And generally it is diminishing returns. You can use gravity is equal to 10, and generally the maths is really easy. You can use gravity is equal to 9.8. Your result becomes 2% more accurate if you do that. It may be worth it. It's not hugely difficult. You may deem, yep, 2%'s worth it. I'm going to use 9.80. But I also just told you that the gravity at your local basketball court is not 9.80. Is it worth going to your local basketball court and measuring the exact gravity via some form of experiment? Yeah, probably not. Hey, that's really difficult. I wouldn't do that. I'd just use 9.80 and I'd run with it. So you're generally getting, as you improve your model, you're doing way more work to get to a high level model, and your accuracy is going up by smaller and smaller amounts each time. In general, not always. So your model is only as good as your worst assumption. There is no point going and calculating gravity at your local basketball court if you're still ignoring drag, because drag's a way bigger assumption at this stage. So you want to understand these assumptions and go, in what order should I be looking at trying to address these to become more accurate? And do I need it? If your robot is nailing threes left, right, and center, who cares? It does its job. Your job as an engineer is to do things that make people's lives better. If it's already doing that, then it's already doing that. Investing more time, effort, and resources into doing it better may not be worth it. This is a little bit of an aside, but it's something that always gets to me. Don't quote a number more accurate than your worst assumption. So you can get your calculator to spit out the range of the ball that Dylan threw to 9 decimal places down to the micron. But if you're ignoring drag, don't write 20 significant figures. If you only knew your initial velocity was 5, plus or minus half, like somewhere between 4 and 6, and we said 5, you've got one significant figure of accuracy in your initial conditions. Your answer can't have more than that, okay? So be aware. Communicate with people. This is the number I got, but this is the size of the error margins that are around it. They're not necessarily statistical error margins. Your statistical error may be low, but if your model doesn't include something, you may want to communicate that with people, okay? And writing down an answer with 10 decimal places does imply you know it accurate to that level. That's just a stickler. All right, so continuing to hopefully make this make sense to you, let's do a couple more examples. So these were our assumptions that we had up before. And we've already been running through the example of shooting hoops. Just to give you some numbers around that, the ball's a little bit over 9 inches in diameter. We're shooting into an 18-inch hoop. Assuming we're trying to swish, not hit the ring at all, we got about 100 mil in any direction of clearance, roughly. What of these things, if we're using our base projectile motion, what of these things would we need to compensate for in order to make sure that we could sink a basket? Maybe drag. Probably a simple drag model would be good. Gravity equal to 9.8 is probably good enough. Flat Earth is fine. 2D assumption is fine, unless you're putting an enormous amount of spin on a basketball with something like the Magnus effect. By the way, if you haven't seen, I'm pretty sure it's called the Magnus effect, where they throw basketballs off of dams and stuff. It's really cool. Go look up some YouTube videos on it after my lecture. You don't need to compensate for relativity. You're doing fine at the speed you're throwing basketballs. Measurement and initial conditions. This is interesting. How accurately do you know how far away the hoop is? Basketball courts are highly regulated. The distance to a free throw line, to a hoop, a height, a diameter, and everything is incredibly accurately set. So you know these conditions really, really accurately in this case. And your initial conditions are based on how reliably your robot can throw. Does it throw at the same velocity every time? If you turn it up by 10%, does its velocity go up by exactly 10%? They're your initial conditions. Cool. So, shooting basketball, projectile motion model, pretty good. Wrong, but pretty good. Second example, still projectile motion. All of these are going to be projectile motion. Now you're doing the longest sniper shot that anybody's ever made, or at least that I could find in my 2-minute internet search. So, what's important now? Is drag valid? A no drag model, I would say, is certainly not valid. Not only is drag in the direction of flight important, but wind moving the projectile sideways is also really important, right? That, which also tells us our 2-dimensional assumption is probably also broken. We probably have to be solving in 3D. Gravity, we will experience bullet drop. I would think 9.80 is probably good enough, but I'm not entirely sure. Flat Earth, not okay. Not only may you have to compensate over 3.5 kilometers for the curvature of the Earth, but even more interesting. Okay, you get an object, like our planet, that is spinning. A particle or a person or whatever on the equator is moving much, much faster rotationally. So they're displacing much faster. The rotation is the same number of radians per second, but their kilometer an hour travel is much faster than somebody up here on a pole, right? So if you move from the outside of a diameter of a rotating thing in towards the center, you'll experience a perceived acceleration. It's Coriolis acceleration, and in small scales like coal washeries and stuff, it's really noticeable. But over that distance, it is actually like this far. I think it's like 2 foot. I did the numbers like 3 or 4 years ago, and I can't exactly remember what they are, but it was enough. If you had to be accurate to within this far, it was actually enough that it would make you miss. So not only is the Earth flat a problem, but the fact that it is a ball that is spinning, that assumption was also needed to be included in order for this to be accurate. Classical physics, bullets are much faster than basketballs. They're still not fast compared to the speed of light. Doesn't matter. Measurement and initial conditions. We knew our basketball hoop was exact distance away. Do we know how far away the thing we're shooting at is? Maybe, maybe not. They do have some pretty accurate laser guided rangefinder stuff, so maybe you know it really accurately. If you're just eyeballing it down a pair of iron sights, maybe you don't. And initial conditions would be something like, does every single bullet in my clip fire in exactly the same way? Okay? Maybe they do, maybe they don't. I don't know. I know very little about guns. All right, third example. So these are two kind of ground-based examples that both ended up with some pretty different levels of sophistication of the model that was required. Third example is going to be the Pioneer anomaly. So I don't know if anybody's ever heard of this, but there's Pioneer spacecraft. They're some of the older spacecraft that they sent out of the solar system. So I'm pretty sure the Pioneer that I'm talking about is... so there's the Voyagers and the Pioneers. I do get these a little bit confused as to which one's which, but the one I'm talking about is like twice as far away as Pluto. So it's like really far out. And we can still talk to it. So because we can still talk to it, in order to do this over such large distances, you need to send a signal to exactly it. And as a result, we could basically know where it is very, very, very accurately. We know how far away it is, and we know where it is in space very accurately. And something interesting happened. As it was floating out in space, it started to drift to the side, and we were able to track it. And when I say we, I played no part in this. The human race was able to track it. Some incredibly smart people were able to track it, and they were able to determine that it was drifting to the side of where they expected it to be. Not a lot, really slowly, but enormous distances out, and they could track it. It took them ages to work out what was wrong with their assumptions. So this is a projectile motion problem. Drag. No drag. You're in the middle of space. There's nothing there to cause drag. Gravity? No gravity. You're in microgravity. You're in space. Flat Earth? No one cares. You're in space. 2D? Yeah, pretty good. I think, they are obviously doing 3D things, and that was the problem. It was drifting sideways. So we know that there was something affecting the 2D assumption. Measurement conditions and initial conditions, well, they knew where they launched it from, and they could track it incredibly accurately, so they knew where it was. It wasn't that. What's this? What it was an asymmetric projectile. The spacecraft has a power source. The power source has a radiator. The radiator would get hot, and it would emit radiation. That's how things get hot. They heat up. They lose energy via radiation. Photons don't have mass, but they do have momentum. So it was emitting light, and the emission of that light was changing the momentum of the aircraft, and that was moving it to the side. That's what it was. And that is just incredible that somebody could figure that out. It boggles my mind. It is so cool. But it was an assumption that was being made that wasn't valid. And that's what turned out to be the thing. So this is kind of one of the cool things about models and assumptions. Depending on your scenario, yeah, you're always wrong, but sometimes it matters and sometimes it doesn't. And if you go and try and, figure out how much radiation your basketball is emitting before you calculate how to throw it, that's not going to be very useful to you. Cool. All right. So this does beg the question. You're a lot smarter than I am, and you know that there's an equation for drag. And I just told you that you can calculate for relativity, and you can calculate for all these things. And you're a lot smarter than me, so you're just going to solve it all. You're just going to get one model, and you're going to be perfect. You're going to put an equation in for everything, and then you're going to have an exactly correct answer, and you're not going to be wrong. So you jump online, you Google drag on a sphere, and you get given this equation. Force drag is equal to half, that's a rho, not a p, velocity squared CD A. In this case, rho stands for density, V is velocity, I mentioned that. This thing is called a coefficient of drag, and this is area. Okay? Density of air, you can look up. It's about 1 kilogram per meter cubed. It's what you'll find if you look it up. Coefficient of drag, you can look up. Coefficient of drag, you can look up for a sphere, 0.47. And you have the area of your object, I'm assuming. You know your basketball, right? So what do? Well, you chuck that into the equation. So sum of the forces in the x direction equals ma, no longer equal to 0. We now have this equation for force, and we get an acceleration as a function of velocity. And we try and integrate this, and we're integrating velocity, which is a function of time, with respect to time. This is actually solvable. You can actually solve this. It's called the differential equation, and when you do it again, you will get displacement as a function of velocity, or displacement as a function of itself. They're called differential equations. You will learn how to solve them in maths in second semester first year, or first semester third year, something like that. You'll learn how to solve them. They're super common in engineering. We see them in all fields, whether it's fluid dynamics, which is what this is. A whole heap of electrical uses them all the time. Heaps of environmental stuff uses them all the time. They're everywhere. You'll 100% see differential equations and vector calculus. That's what this is, and this is like 80% of engineering maths. And you can solve that. You might have to learn some maths, but fine, you can solve that. And you're a hero, you've got it, you've solved it. Well done. Except, of course you haven't. Of course not. It's not that easy. Your coefficient of drag is actually a function of this thing called the Reynolds number. So whilst it is about a half for some values of your Reynolds number, it's not for a whole bunch of other ones. And your Reynolds number, it turns out, is a function of your velocity, which is in your drag equation. So that changes with that, which changes with that, which changes with that. It's all circular. And even worse is it depends on the surface roughness of your object. And in order to get these graphs, this was NASA. Okay, so this is not the simplest stuff to get in the world. It took NASA to build these for even a sphere. And they only did it for 2 different surface roughnesses. So if your basketball doesn't have one of the particular surface roughnesses of the 2 things that NASA tested, you need to call them up and go, hey, can I put this in your hypersonic wind tunnel, please? To which they will say, no. Awesome. So we get to the end of that. We realize that this is horribly complicated, and you can do an entire PhD in the turbulent flow behind a sphere, and many people have it. Is that unbelievably complicated? But let's move on to area. Which area? Cross-sectional, cut through the middle, or surface? That's not the greatest image to represent those 2 things, but cut through the middle or surface area. Which one? Well, turns out that depends on what type of drag you're talking about. One of them depends on the cross-sectional and one depends on the surface roughness. This is partly why there was 2 different plots, but more there are multiple forms of drag. And depending on your object, different ones dominate. So now you got to call NASA again. They're getting sick of you. Basically, the point of my story is it's turtles all the way down. Every time you get to a thing, you can generally find an equation that describes it better. But if you get to that equation, you'll realize it's built on a bunch of assumptions as well. And once you open that up, you realize that's built on 5 other assumptions. And you can just keep chasing these things forever. And that's what we do a lot of the time in science. So this is a cool quote from it's a prelude thing from a physics book. It says, we've basically got physics sorted out, except for the big stuff, the small stuff, the hot stuff, the cold stuff, turbulence, and the concept of time. But, other than that, we're pretty much there. And as I said, that's mainly what people, not mainly, but a big thing that you can do in a PhD, is you just track one of these things all the way down. there's some cool people around here who I'm hoping to get in to tell some cool stories about more or less doing this type of stuff. Just for funsies, here's some more things that we haven't even considered yet. We have our object is moving through the air, and the air is imparting force on our object. That's how we get drag, which means our object's also imparting a force on the air. And if you put force on air, it compresses, which changes its density, which was one of our parameters in our equation, but that also changes its temperature, which also changes its density. And again, we get caught in a whole nother circular loop there. And also, as you get closer and closer to the speed of sound, this can become hugely problematic, and all the physics that we normally have around this begins to break down, and we need totally new sets of models that are not compatible. The ones that work at and around the speed of sound do not work at and around low velocities, what we're talking about here with throwing balls and stuff like that. Also, if you want to get into the aerodynamic side of this, I watched a lecture just a couple of days ago. It was really cool. It's this old professor guy, and he talks about basically misconceptions in the understanding of aerodynamics. I'll link it down below in the description. Don't try and follow the maths in it. I didn't follow all the maths in it, but it's a really interesting highlight of just looking at some of the really complicated physics around the concept of lift, okay? Because like lift is like drag, but it's way, way worse. Okay. If all of this is too airy-fairy and you want a concrete example of why your basketball model is wrong, it's because basketballs are not defined by a diameter. They are defined by a circumference. I didn't know until I had to look this up. And so to get a diameter, I had to divide my circumference by pi. And because pi is infinite and the amount of computational power I have access to me to do this calculation is limited, somewhere I cut pi off and I made an assumption. There's some aspect left of that that is wrong because of when I rounded pi. And that is inescapable, right? Now that is minusculely small, but that is inescapable. Pi is infinite, my diameter is wrong. And so everything that relies on a diameter is wrong. Doesn't matter, we can use it anyway. So, let's round back. Assumptions as an engineer. Our job isn't to be perfectly right at all times. Our job is to solve problems. So we make assumptions all the time because trying to make a perfect answer to this would take an infinite amount of complexity and we'd never get anywhere, okay? We have to make assumptions. There's no escaping it. I really love this quote. Anyone can make a bridge that stands. It takes an engineer to make a bridge that just stands. Great engineering is knowing not how to make something necessarily stronger, but how to remove material, how to have less of an environmental impact, and yet still do the job that we need to do. There should be some pictures appearing now. There we go. So, two different bridges. An older style bridge, stone arch bridge. Really inefficient use of material. There is way more material there than there needs to be. New modern bridge with truss elements all the way through it and this really elaborate design spans an enormous distance, right? Using relatively an incredibly small amount of material and thus consumed an incredibly small amount of the world's resources to make by comparison to this design. Okay? So the better your model, and that's what was needed here. They had better models, they did more design work, and so they made a smarter bridge. So the design work there is way more expensive and required computers and stuff like that. Not possible whenever this bridge was built 100 years ago. But that's what we do as engineers. We make better models, we push things forward, we make better models, we make models more accessible, and we can do better design. But it comes at the cost of increased complexity. This bridge here would have a significantly lower safety factor than this. Safety factors are get out of jail free cards to say my model's crap, so I'm banging a big safety factor on it. Which is fine. There is nothing wrong with that, but that's essentially what safety factors are for. If you had a perfect model, you would have a safety factor of 1 and nothing else. Not that you'll ever get a perfect model because we just discussed why it's turtles all the way down. You don't have a hope. There are some models that you will find that are better in different scenarios. So sometimes a really simple model is all you need. A back of the envelope calculation, we call it in engineering, something that you can do really simply with really basic models to let you know roughly, are we going to be okay in this space? And a lot of the time, that's all you need. You don't need anything more complex, and you shouldn't do anything more complex than you need. In other cases, you want to go really high complexity. You'll also find different situations, and I think I'm going to allude to this later, but there's some situations where a certain way of modeling is really good, and some situations where different models are really good. I alluded to it earlier. When I was talking about the drag models as you get close to the speed of sound, the models that we have that work really well around the speed of sound are not totally contradictory, but they're not the same as the models we use at normal people's velocities. Okay, so different situations requiring different modeling techniques. You need to understand the models that you are using. You need to understand the assumptions that are based upon, so when you push the limits of them, you understand what you are doing. Sometimes these things are valid, other times they are not. It is on you to know when they are and when they aren't. You don't get to black box this stuff and just say, this is what was in the textbook, so that's what I'm using. Not at a first year level, but as a professional. And as you upskill throughout your degree, you will learn how to make more and more advanced models, and eventually a really high level skill for as an engineer is to know when to use which models. Communication is critically important through this process. All right, you need people to know what types of models you are using and making. Cool, awesome. That's most of the content around models. I'm going to tie a few things back together and do a few disclaimers for the next little while. So there's another couple of slides on models, and then we'll jump into units. All right. So wrong versus incomplete models. This is me clarifying something. I did say all of your models are wrong, and they are, but I would say it'd be far more correct to call our projectile motion incomplete rather than just calling it wrong. It's true, but there are other bits that it's kind of missing. It's a simplification, okay? As literally every model on Earth, no matter how advanced they are still simplifications of our universe. There are, however, some models that are flat out wrong. So again, how do aeroplanes fly? This is what that video about aerodynamics in. It's a 40-minute lecture on all the things that we think we know about aerodynamics being wrong, and how unbelievably complicated flight actually is. And there is a method that is taught in schools to this day, I believe, at least when I went through it was, and it's called equal transit time. Well, the equal transit time theory. And it is flat out wrong. It is not incomplete, it's flat out wrong. And there's a whole bunch of stuff that can prove it, and if you're in mechanical or aero, we will show you the videos that fundamentally prove equal transit theory is wrong. It's in syllabuses and stuff. It's wrong. There's another explanation that says Bernoulli's principle and pinching and stream tube pinching. And it's not wrong, it's incomplete. Okay, so there are some subtle differences. So, using wrong as a catch-all is, we should probably have a little bit more fidelity, and now we do. Wrong versus incomplete. Yeah, this is where I was talking, this is when I said it was going to come up. Models being contradictory and still useful. That can totally be a thing, depending on your scenario. There's a good one with rockets. So you can look at how a rocket works, how a rocket flies via Newton's laws of motion, which should be possible, but is incredibly difficult. There's a really simple way, and it's a totally different approach to modeling. Instead of looking at thrust and stuff from Newton's 3 laws, we look at it from a conservation of momentum perspective, and we say hot exhaust gas was ejected backwards with a mass and a velocity, meaning it has a momentum. In order for conservation of momentum to hold, our system as a whole thus needs to displace forwards with the same momentum. We know its mass, therefore we can calculate the velocity that it will be moving forward at. And so it's just a totally different approach to the same problem. And you will see this all the time, okay? So there's not one way to model something. Hope is kind of clear from the stuff that we've spoken about. The other disclaimer is if you're a pure mathematician, yeah, I could give you an argument that says your models aren't wrong. They are potentially. No, a pure mathematician, yes, your models are correct. It's just your application to the known universe where the problems become. You know. I would say on this graph, by the way, engineers sit somewhere between chemists and biologists, but that's just an opinion of mine. All right, in order to use these models as an engineer and be successful, we need to really understand the problems that we are solving. So next week in the lecture, we're going to spend a lot of time on problem identification. And I just want to make a blatantly obvious tie-in between the models and assumptions that you're going to use and understanding the problem you are actually solving so that you can figure out how many resources you have to dedicate to how complex of a model you need in order to help somebody and solve your real problem. Nice explicit plug for next week's lecture. Okay, so remember, there are discipline-specific videos to contextualize some of this knowledge, even if you didn't find projectile motion particularly applicable to you. I also don't care. You need to know it because you need to understand, no matter what engineer you are, the models that other engineers use. Okay? So, yeah, you need to understand models across disciplines to be successful. There are some theories of modeling that are a little bit different to the way we've shown projectile motion. That they would model energy, and one of the reasons they're very successful modeling styles is because energy flows through virtually any engineering system. Doesn't matter whether it's engineering in a energy in a person being conveyed into electrical energy, into kinetic energy, into a machine, into a motor, into whatever. It's energy flowing and generally energy being controlled by computer programs and scripts and stuff that all of this kind of works together. These are called bond graphs, and they are joining, in this case, a mechanical pump in a civil dam driven by an electrical motor controlled by a mechatronics solution. Yeah. So modeling across disciplines is incredibly important. Everything is connected. None of us work in isolation in the real world. I spend more time working as a mechanical with chemicals and mechas than I do with other mechanical engineers. So it's a thing. All right, code. So if we look at this from a bit of a coding perspective, I understand that there's some softwares consuming this, and there's some people a lot of people doing Eng 1003 at the moment. Let's have a look at some real world stuff and try to marry it up with a bit of code. This is really difficult to do because you've got all your real world assumptions and then you've got all the extra assumptions for when you implement something into code. I used to use this example because you used to use C, the programming language C, before Python. This is the first year of Python, by the way, in case you didn't know. Python's great because it treats every number in it as I believe, a double. You don't have to declare numbers as integers or doubles. In C, you did. What this means is when you get a number, you have to tell it whether it's going to be a whole number or whether it's going to be a decimal number. Takes a lot more computing power to deal with decimal numbers. So when you have things that you want to make sure are whole numbers, you declare them as integers. So let's do a quick example. How many teams do I have in Eng 1500? Well, let's say I have 100 students. I have 700 students, but who cares for the purpose of our example. Let's say I have 100 students and I've got 4-person teams, and I know I can't have a half a student in a class, and I can't have a half a team. So I just go number of students as an integer, because I can't have half a student, divided by size of team as an integer, because I can't have half a team, and I'll get my number of teams. Happy days, right? And I have 100 students, 4-person teams, 25 teams, golden. New person enrolls. Now I've got 101 students. This equation, doing integer mathematics, gives me 100. 101 divided by 4 is... Sorry, it doesn't give me 100, it gives me 25. I apologize. 101 divided by 4 equals 25. 102 divided by 4 equals 25. 103 divided by 4 equals 25. Not 25 and a quarter, not 25 and 3/4. It doesn't round. It is 25. okay? And obviously I can be in a lot of trouble there because I need to be resourcing an extra team. There's people kicking around, but there's nothing for them. Now, all right, let's assume they're not teams. Let's assume they are a number of lifeboats that need to be on sinking ship. Oh no, you just drowned 3 people because you messed up integer and double. You made an assumption. The assumption wasn't valid. Problem. Yeah? So it's the same. It's the same logic that we were talking about before. There's nothing new here. It's just another tier of assumptions. And this can be particularly problematic. It's really important for software engineers because they're often handed things to do, say, code this for me, and there's no real discussion of the assumptions and the models on which it is built and how they will be transferred into code. And that's why we get things that sometimes fall out and go, oh, a shitty bit of programming there. It wasn't. They programmed the thing you told them to, but they didn't understand the models and assumptions. So as a software, you have to understand that, and other people need to communicate it better. Comments are great, all right? To try to explain what you are trying to achieve with your code in simple English can be really beneficial, so that you don't end up with hilarious scenarios where the code doesn't do the thing that it's supposed to do. Cool. All right, to kind of wind this section up, assumptions in Eng 1500, you will be required to make a lot of them. Your team will probably make some slightly different assumptions to other teams in your workshop, because once you get to a real person as an end user, you'll have to make a whole bunch of assumptions about your client and a whole bunch of assumptions about the human being using your end product. And that's super important for success in 1500. We'll talk about it next week, but understanding the human at the center of the problem is really important. You assume a different human to me, we're going to get different assumptions and then different models and then different optimums. Work with your client. Talk to your client about your assumptions and your models so that they understand what you are doing. We've kind of spoken about this. Some of your briefs are intentionally ambiguous so that they allow you to select particular models. And starting early before you realize what you're realistically doing can be really problematic. Again, we'll talk about this in exhaustive detail next week. Also, there are occasionally loopholes that you spot in our project briefs that we don't spot. Talk to your clients about them, because if you show up with something that exploits a loophole in the brief that we don't find an acceptable solution, that's still bad for you. If you find a loophole in the brief that's an acceptable solution, 100% nail that thing, go for it, but just keep in contact with your workshop leaders about it, okay? All right, so this is like the last slide for this section. This is normally just a fun thing to do in a big room, is get people to shout out some things that have been historically widely held assumptions that no longer are true. And one of the learning objectives here, and we'll get things like the Earth was flat, that the Earth goes around the Sun, or the Sun goes around the Earth, and all of these types of things. It's normally a bit of fun, but also just remember in a couple hundred years, people are going to look back at us and they're going to laugh at us. And that's good. All right, cool. So models and assumptions was by far the biggest chunk to this lecture. These other 2 bits are a little bit lighter. We're going to go through them pretty quickly, and whilst they are still, some bits of them are still important, this should be a little bit less of a mental load, and they are definitely 2 shorter sections. So, section 2, units. Units in engineering are incredibly important. Generally, I'm talking about measurement and units here. So, I will harp on about these a little bit, and you will find virtually every single one of your academics you ever have will beat into you something about units. Use your units. What are your units? And a lot of the times it didn't, when I was a first year, make any sense to me as to why anyone cared. And at a lot of the first year level, I don't think it does matter that much that you have units on your things, with the exception of you need to build good habits now because it will help you later. And I wish that was what somebody told me. Trust me, it will help you later. You don't know enough to understand why. Build good habits now. So, units are actually useful and they will make your life easier, and that's why we make you do it, even though they may seem burdensome now. The main reason for this is that the units of an equation always balance. And that gives us hints about the answer. So if we have a model, a mathematical model, we can look at it and we can tell things about answers or variables or whatever based on the units that they have. For example, we were calculating range, right? That was one of our things that we were doing before. We were trying to work out whether our basketball would go a particular distance. If we do that calculation and we track our units the entire way through, remember some of that math was differential equations, right? You may not have seen them before. You may get them wrong the first time you do them. Did your units come out in meters? If so, you may be correct. If they're not coming out in meters, you definitely messed up somewhere. When the math gets tricky, this is super useful to have a cheat sheet in your pocket here, which is track your units. All right, so this is an important slide. This is going to be the example that I demonstrate this. I took this example from Simon Iverson's lecture notes. I'd put an example together the first year I ran this, and then I saw Simon's, and it was better, so now I use it. If you are in chemical and renewable, you may see this with Simon. He will do a better job than me, but for everybody else, you get me. Awesome. So, a 100-watt light globe shining 8 hours a day, 5 days a week for 52 weeks, which is 1 year, by the way, consumes how much energy? Well, we chuck all the things in. Energy, 100 watts, so that's 100 joules per second. That's a watt is a joule per second. 8 hours a day, 5 days a week, 52 weeks. 208,000. I would expect this to be a big number. That's a pretty big number. That seems reasonable. It's wrong, but it seems reasonable. If we look through and we cancel our units out, weeks cancel with weeks, days cancels with days, but hours don't cancel with seconds. Our units are actually joule hour seconds. Our unit should be joules. This should be an amount of energy, and it should be joules, because joules are a measure of energy. So the joules are good. The hours seconds are not good. What do we miss? Well, we miss the fact that there are 3,600 seconds in an hour. We never compensated for that anywhere. A watt is a joule per second. We need to add in how many seconds are in an hour. And if we do that, now all of our units cancel, happy days, we end up with an even bigger number with the units of joules, and this one is correct. Okay? So, you get into these types of problems, you don't have a great feel for the answer, you track your units. Yes, it was more work to write all the units down, but hey, now we're right, and it's worth being right. So, units always balance in an equation, super useful. Also useful, you can only add and subtract things of the same unit. So if you're not sure, you can't subtract seconds from joules. That's just not a thing that you're allowed to do. So it gives you hints about equations, lets you know how to work with them. And if in doubt, try whatever you can to stick with one unit system. Mixing seconds, hours, days, weeks, when you are trying to talk about time, generally causes you problems. So I mentioned sticking with SI units. What are SI units? They're a standard set of units that allow you to measure all physical phenomena in the universe. And in order to do that, you actually need 7 of them. And that's it, which is quite interesting. So I asked you again in the worksheet to think about some of the units that you need. So try and keep with me here. What units do you have for these particular variables? And are there any that I don't mention? So distance in meters. Pretty unsurprisingly. Mass in kilograms. Good. Not grams. Kilograms, by the way, is the SI unit. Time in seconds. That's not meant to say seconds there. It's meant to say seconds there. But time is in seconds. It's not in minutes, hours, days, whatever. It's in seconds. All good. Temperature in Kelvin. Not in Celsius. Kelvin. Definitely not in Fahrenheit. Kelvin. A Kelvin and a Celsius are the same size, but while Celsius is 0 is the freezing point of water, Kelvin 0 is absolute 0, no atomic motion, the coldest you can get, about minus 273 degrees Celsius. Current, so this is for your electricals, current is measured in amps. Uh, chemicals left? Yes. The amount of a substance generally used in chemistry is a mole. It tells you you've got 1 mole of water or 1 mole of steel or whatever, based on how the number of atoms you have. And luminosity in candela. I've never used this unit, and I think that there are probably better ones, and I've never fully understood this bit, but it's always tacked on the end. And okay, luminosity in candela. You must need it in some scenarios. Now, I would assume if you thought about all of the units that there were more than this, and we see them. We used newtons before. But if we remember, F equals ma, force equals mass times acceleration. So newtons is the unit that you know. It is the unit of force, but mass is kilos, and acceleration is meters per second squared. So a newton is simply a kilogram meter per second squared. They're the same thing. You don't necessarily need the newton because you have these other units. All right. So any other unit you know can be derived from the units that are here. Volts can be derived by current and time and stuff like that. Like you can work out any of them. Pressure measured in pascals is force divided by area. Force we know is a kilogram meter per second squared, and area is in meters squared. So this can get really complicated really quickly, but it can be useful to know these unit conversions, because sometimes remember that units will cancel out, and you may have some gigantic, ugly looking thing and realize, oh, hold on, that's just a Pascal. Boom, done, problem solved. So this is just ripped from Wikipedia. There's a whole bunch of different unit conversions in there. The Wikipedia article for units is really good. So if you get confused, go to Wikipedia. It's great. Also, there's funny jokes about units. They're great. Tell your friends. They'll definitely laugh. All right. So we've done a calculation. We've got some units out at the end. A really good thing for you to check is, do they make any sense? We could check before. Remember in our other example, we expected joules and we got something that wasn't joules. So we could realize that we'd probably made an algebraic mistake somewhere. And you can do this pretty much any time you ever solve a problem, provided you carry your units through. It's a nice check. Not only do they have units, but most units have a sign as well, so a positive or a negative. So if I was to take force as an example, can I have a negative force? Does that make any sense for a force to be negative? Well, yeah. I can have gravitational force pushing something down and the table responding on it, pushing it back up. I've got two forces in two different directions, depending on my coordinate system. One's positive, one's negative. It's fine. There's nothing wrong with that. This can get complicated really quickly, though. So if you get into multi-system pulleys and blocks sitting on blocks connected to pulleys to other pulleys back to the same blocks, it can get really complicated, and it can start to become incredibly hard to rationalize this out in your head. So again, being meticulous and having good habits and carrying everything through, this will just sort of fall out in the end, and hopefully it'll all make sense, and it will make analyzing complex systems easier. Also, disclaimer, ropes, pulleys, I can put rope into tension, right? Very strong. What happens if I put rope into compression? Doesn't do anything. Ropes don't transmit force in compression. So tracking this type of thing, being very careful, realizing at some stage in your system that you would need a rope to be in compression for it to work, means it doesn't work. So really useful stuff that you can derive from your systems. But negative force in general is possible. Negative mass, however, not so much. You've probably broken, at least not in the universe in which I live. I don't know where you do your maths, but in my universe, generally having a negative mass is bad. However, simulations will often let you do this. All right, a piece of simulation software that I use for doing crystallography stuff has a parameter that talks about the amount that an atom vibrates away from its initial spot as it heats up. It's centralized around an initial spot, but it moves randomly. The program will let that number go less than 0. So it moves less than a 0 distance away from where it started. It does not make any sense. But the program is perfectly happy for you to do that. So these are the scenarios where you need to engage your brain and make sure you're not doing something that's physically impossible. Whilst at this level, again, you can probably just do that in your head and you're like, who cares? I can just look at it and know the answer. That's fair. But once you get into thermodynamics, fluid dynamics, and quantum mechanics, yeah, that's not going to work for you anymore. So being meticulous is super useful. All right, that's kind of in SI units. There are other types of units that we use. Metric are probably the ones that you've heard about. Um, and it's because SI is not always the most convenient. If I was to ask you how far away you live from university, I live 15 kilometers away. I don't say I live 1,500 meters away. I say I live 15 k's because kilometers are a more useful unit of distance a lot of the time than meters are. If you want to talk to me about my crystallography and ask me the distance between two aluminium atoms in my energy drink can, I'll say they're 0.47 nanometers apart on average, something like that. I won't tell you they're 0.00000000047 meters apart because that's dumb and too many zeros. Okay, so we often use metric units. Now, the trick with metric units, these are acceptable. They're often called engineering units as well. Again, it's kind of dumb. You just call them metric units, but whatever. 10 to the power of 3 is the secret. So you are 1,000 times bigger or 1,000 times smaller, or 1,000 or a million or a billion, 10 to the 3, 10 to the 6, 10 to the 9, or inversely back the other way. That's it. All right. You don't mix anything else other than that. So centimeters are for dressmakers and measuring the size of the fish you just caught. They're not an engineering or a metric unit to use centimeters. Okay. I always find funny whenever I see the meme ragging on the Americans going, "Oh, use metric units like centimeters." Centimeters aren't metric, but anyway. So just another situation where metric units can be super useful. The SI unit for pressure is the Pascal, so it's 1 Newton per square meter, which is really small. So a square meter is quite big, and a Newton's a particularly low force, so it's a really, really small unit. If you want to talk about stressing a piece of material and how much stress or pressure it takes to snap a piece of steel, for example, you're going to be in the hundreds of millions to thousands of millions or billions of pascals. And the units that we use to measure the cross-sectional area of most pieces of steel and stuff like that isn't meters. We don't use square meters to determine these dimensions. We generally use millimeters. So if you use millimeters and you use newtons, your measurement of stress falls out to be megapascals, which is actually a really convenient unit of measurement. So you'll see engineers will work in millimeters, megapascals quite a lot. Just a thing that we do. You'll see it. It's super useful. All right. So I already gave a little bit to the Imperial system, and whilst there are some faults, let's talk about where the Imperial system came from and why it's actually brilliant. If I asked you to tell me how wide the room I'm in, or how long your backyard is, or how far your driveway is, or something like that, what would you do? You'd almost certainly pace it out, right? And that's a really convenient, really easy way to do it. But if you've ever tried to pace out meters, it's a bit further than a nice, comfortable step. A yard's a really nice, comfortable step, though. That's why it's that long, because it's super easy and super useful for regular Joe person who needs to do a thing, okay? And that's where Imperial units come from. They come from a human being needing to do a job, not a scientific job, but a normal job, all right? If you watch the Adam Savage video, if you didn't watch the Adam Savage video, it's in the description below. Watch the Adam Savage video. It's fantastic. If you did, he knew this guy in ancient Greece needed to know the distance between two cities. He knew it very accurately. The way he knew it very accurately was because the Romans were very, very systematic about their imperial units. The Roman foot was exactly 10 inches, not 12 like it is now, and it was the standard size of a standard issue military boot, which means every soldier could measure it very accurately. A pace was 5 feet or 2.5 steps of an average soldier. So this was very, very accurate way. If you marched a bunch of soldiers from one place to another, they had a standard stride as they marched, because that's what marching is, and then you could get very, very accurate distances over incredibly long ways. This is super useful. This is my favorite unit of all time, and it is an acre in the Middle Ages was defined by the amount of land that a yoke of oxen could plow in a day, which is hilarious. And it sounds ridiculous. But to a farmer, what they needed to know at harvest time or plowing time or whatever was less exactly the square number of meters they had, but how many resources they needed to work the land. That was the useful unit to them. Again, they had a problem to solve. It's not the same one as the one you're generally solving, but that was their problem, and that's why it was a useful unit. I mean, it's hilarious that if you move to a different city or countryside and its soil had a different strength, the size of an acre was different depending on where you lived. And the British hated that, because they were trying to map the entire world and claim terra nullius and do whatever they were doing and draw lines and put fences up and make borders, because colony. So they standardized a bunch of these units, and they standardized them around some not so great things to use as standards. So the redefined acre. It is defined by an area of one chain, which is 66 feet, by one furlong, which is 660 feet, which is equal to 1 on 640 of a square mile, or 43,560 square feet, approximately 4,047 square meters, or 40% of a hectare. Fantastic. It's an awful unit now. It's still there because history. And if we want to look at all of the different ways to measure length in an imperial system, we get this. And it's a mess. It's an absolute mess. Like, some of these things were real useful. Poppy seed is about 1 millimeter long. Hey, I've got a bunch of poppy seeds. I can measure things kind of accurately. But you can't do science with that. You can't. And you should stop. And the French did. And they just went, no, this is dumb. And after lopping a bunch of people's heads off, they also redefined a measurement system so that they could do science with it. And that's where SI comes from. So, most of the world slowly followed the French in this. And so these types of maps are always funny to see in the couple of countries that didn't. But to give you a little bit of context, some of this is due to what's called a lock-in effect. If you're already set up in one system, swapping to a new system, it's called a switching cost, maybe doesn't necessarily outweigh the original cost. I grabbed some numbers, NASA to switch itself over, and I would say in the entirety of the United States, the thing that is closest to metric is NASA. And their internal cost to switch would have been $370 million. I saw some numbers on what it would cost the US to switch, and they're talking tens of trillions is what they're estimating it at. So, that's money that you're not putting into schools and hospitals while you're switching all your road signs over. And that's political suicide. So, this is the size of the thing. That being said, it cost them some money too from that time that they ruined a Mars probe because they mixed their units up. So it has costs, but yeah, interesting. All right, so the United States is still imperial, and we also are still imperial in a lot of ways. Whilst we are officially metric, you will find that we're not in all sorts of different applications. So if you go and try and buy pipe, and I bought pipe not that long ago, I couldn't buy 200 millimeter pipe. I literally couldn't buy it. That's what I wanted, couldn't get it. I could get 203.8 mil pipe though, because it's 8 inches. We're not really metric, are we? Can't buy 200, but you can buy 203. Every PCB we've made, so printed circuit board, so that's in every one of your computers, every kit that we've given out in Eng 1500, every single one of those PCBs is imperial. None of them are metric. They've got sometimes metric dimensions on them, but they're like 54 point something millimeters, because they are actually imperial. So you will encounter this all the time. Walk into a workshop, get a piece of round bar. It will not be 20 mils, it will be 19. So you need to know a few of these things. So an inch, these is the most common ones. An inch is 25.4 millimeters. A half inch is 12.7. A quarter is 6.35. So you're in danger zone here, because sometimes you'll get stuff that will fit quarter and won't fit 6. So this can be tricky. As I said, 3/4 is almost bang on 19, and 5/8 is almost bang on 16. They're really close. A foot, 12 inches, 305-ish mil. A pound, 2.2 pounds to a kilo is another super useful one. So you got to do pounds and kilos, just halve it or double it, and you're there or thereabouts. All right, so on the other side of the coin, if these Imperial units are so bad and have been given crap to them, it's only fair that we give some crap to the other side. Does anyone know, this is normally my question to the crowd, does anyone know how the meter is defined, or how it was originally defined? You want a real useful unit, you want the meter, it's great, right? It's 10 millionth of the distance between the equator and the North Pole. Cool. Thanks. But it's alright, because what they did was made a bar, and they put it in France, and I don't know, then there was the standard meter bar. It was wrong, so they had to make a new one, which was also wrong, and then they had to make another one after that. But then they had a bar, and that was great. And there was one bar in France that, I don't know, you could come and calibrate your meter ruler against or something. And then, after a little bit while, when some lab stuff got quite a lot better, is redefined as a number of wavelengths coming from a Krypton 86 lamp. So if you've got one of them, you can calibrate your meter ruler with that. And then it was redefined again as the distance light travels in that much, which is roughly 1/300 millionth of a second, which again, I don't have a laser that can measure that, but okay, somebody might. Yeah, it's not a great unit, hey. The meter itself is just as dumb as any other unit. It's the system that was built around it that was good. But if the meter's not great, maybe some of the other ones are a bit easier. What about the second, or the kilogram? Well, that's the kilogram. It's a lump of steel in France again, so we're not getting any luck there. And the second is the number of time elapsed by that many cycles of the radiation produced by the transition between two levels of the cesium-133 atom. Cool. So it's not the units themselves that are important, it's the system that they were built around that's important. That's the advantage, okay? The units themselves are just as arbitrary as any of the British ones. Cool. So just some interesting backstory on them. These things are called cesium clocks, by the way, and they're uber accurate. Super cool. All right, exiting out of some of the random fun stuff, white slides are generally, as you can probably tell, important slides. This is going to be a little bit of rules around how to format units, and this is going to be important for you. It sets an impression to a reader about how much engineering you know is basically based on how well you know how to format units, okay? And like it or not, and we'll talk about this in week 4, but like it or not, the way you format things biases your reader into how much they trust you. So if you want them to think that you are smart, you need to learn how to format units correctly. You don't have to like it, you just have to do it. All right, so first up, learn the correct abbreviations. It's S for seconds, not sec. Learn what they are, all right? If you don't know, look them up, and there's a link in the description below on a really good site with all of these rules in it. But never use sec for seconds. That's like amateurs 101. All right, this one's another one that's pretty well commonly known. You capitalize units named after people, you don't capitalize other units. So the Newton was named after a person, so you capitalize the N. Meters were not, amperes were, seconds were not. All right? If you don't know, again, look them up. It's generally pretty simple. This gets significantly more complicated when you write out sentences, because you don't want to confuse the name of the unit with the name of the person, and thus, although the unit of power is the watt, we're talking about the unit, so the first watt is not capitalized. It is named after the person watt, this is now a proper noun, so it is capitalized, and it is given the symbol capital W because the abbreviation is capital because it's named after a person, even though when we write it out in full, it is not. You with me? Good. Moving on. Kelvin also gets capitalized in both cases because of reasons. And sometimes the letters in L, even though it's not named after a person when it is abbreviated, is sometimes capitalized. Because it gets confused with a 1 when it's lowercase in certain fonts. Depending on who you ask, not everybody accepts this. Generally, we capitalize prefixes that mean bigger, and lowercase for prefixes that mean smaller. Mega, 10 to the 6, versus milli, 10 to the minus 3. Yes, one means a million times bigger, one means 1,000 times smaller. The bigger one gets the capital, the little one gets the lowercase. With the exception of the kilogram, which is lowercase, even though it means bigger. Also, kilograms are the only SI unit which have a prefix. Just in case, you thought you were on top of this, there are layers to this thing. There are rules and there are exceptions everywhere you look. One thing that is a nice unambiguous rule, though, is you should use a space between the units and the number and the units. So when you abbreviate meters down, you are abbreviating the word meters into the letter M. All right? And because you wouldn't write 1 meter without a space, you don't write 1M without a space. So you put a space between your numbers and your units. A lot of people don't like this. I hated this when I was your age. I thought it looked super dumb. But I've so turned around on it, and I'm utterly convinced that this is the correct way to do it. And this one's a pet peeve for me now. I've come full circle. So if you're handing me anything, always go through and make sure that when you proofread, you put spaces between your numbers and your units. You don't put spaces between prefixes and units, though. So meganewtons, there's no space between that. It is one word for meganewtons. There is a thing called a non-breaking space. This is super cool. You put this space in between your numbers and your units. So you would hit 1, Control Shift space, let it go, hit M. And it'll put in a space. It'll look like a normal space, but when you get to the end of a line, it won't push the meters bit onto the next line without taking the 1 with it. So it just helps with a little bit of formatting. It's a little cool trick that I learned fairly recently. All right. This is the number one rule when it comes to formatting in general, and especially when it comes to units. As you can probably see, this can get confusing super quickly. The most important thing is that you are consistent at all times. I will give it to you if you don't put a space between your numbers and your units ever. I'll be like, well, it's wrong, but at least you were consistent. If you're not consistent, that is really bad. Okay? There's a link in the description below with a whole bunch of, I think it's 19 or 22 unit formatting rules. I'm not saying memorize them. I'm never saying memorize them. I'm saying know when to look them up. Okay? That's the important thing. So just to finish off this section, because this section is now done, units are super useful. They will make your life easier. That is why we make you do them all the time. You can make up units out of other units, and they can make your life easier as well, because constantly using SI can be tricky. And formatting is super important and will really matter when you communicate things, written communication with people, and you will learn this throughout your degree. In some circles, it is incredibly important that you get your units correct. You'd be amazed how important it can be in certain circles. Some people don't mind too much, but others really do. All right, so if your workshop leader is stressing units to you, pay attention. Their field cares. Cool. Last section of this presentation, research basics. So you will be doing a bit of research in your projects, and I'm going to sort of take you through how to do that. Not in exhaustive detail, just a little bit of a roadmap so you can kind of know some traps for young players and have a bit of a feel for how it might go. So all your projects will require you to do some research. I would consider what you learn in your workshops, either doing labs or having presentations given to you, that's research. Anytime you're learning new content, either via consuming something somebody else is communicating with you, written, verbal, whatever, reading a textbook, reading an article, having a presentation given to you, that counts as research. And also doing experiments and trying to learn new things That way also counts as research. All of this is research to me. And you'll do a lot of it, you're already doing some of it. Remember, when you start your research, you're not trying to research exactly how to solve something, you're just trying to understand the space in which you are working. The better you understand the space, the easier it will be to solve things in it. So don't try and target your research to, oh, this won't be exactly applicable in my project, I should ignore it. The auxiliary stuff helps as well. Learn as much as you can, it will make your life easier. It is also fairly poorly portrayed in almost all media that you see. So it can be a lot harder and a lot more difficult and a lot slower than people think in order to learn and to understand things in a nice, meticulous, and correct way. And think about, all the models and assumption stuff we talked about earlier. You'll need to do this forevermore, so any content you learn now or skills that you develop of how to do this efficiently will certainly be useful to you in the future. Okay, so to build up our knowledge and our understanding of something, generally we go information, knowledge, understanding is the hierarchy in which I generally address this type of thing. So we start with information. We got to get information from a particular source. You may have heard some things about Wikipedia. As an academic with a PhD and a 10-year research background, how often do I use Wikipedia? Every day. Wikipedia is the greatest, in my opinion, the greatest resource humankind has ever come up with. It is knowledge that is shared at a base level, so there is no barrier to entry. It is free, it is written in plain English so people can understand it, and it covers enormous amounts of content. It is fantastic, okay? And it's way better than stupid, obscure resources that maybe they were peer reviewed in a dodgy article that nobody can access anymore. People give crap to Wikipedia because anyone can edit it, which is great. If I log on and I see some obscure ceramics article that's incorrect, I can update it to make sure it is correct. And that happens far more than trolls putting dumb stuff on there, okay? So, Wikipedia is fantastic, and it is where you should start. And we'll do an example where we start with it. Don't reference it. It's just not done. Okay, it's just not the professional way to do things, is to reference it. And yeah, it could be wrong. Get more than one source. Don't go, I saw it on Wikipedia, therefore it's correct. But that applies to literally everything anyway. I wouldn't, if a single paper said something, I wouldn't trust it if other papers were contradictory to it. You can Google things. I really hope your generation knows how to Google things. But the good thing about Google is directly leading on from the point of get more than one source. Why Googling something is great is it will give you pages and pages and pages, and you can get 20, 30, 40 sources out of Google really easily and look for trends and biases and stuff like that. It is fantastic. Probably one of the best places to get information around something is a user manual or a tutorial. You want to learn how to do something, I guarantee you there's a YouTube video on how to learn how to do that thing. Use that. That's a great resource. User manuals are also great. They're less popular now with the advent of YouTube, but printed user manuals are super good as well. The best place for you to get information is a textbook. The reason being, it is the one resource on this entire list that it will be targeted directly at undergrad students. So a lot of the Wikipedia might be a little bit too light, a little bit too not detailed enough. And if we jump into papers, they're written by experts for experts, so they might be a little bit too dense. Textbooks are a fantastic middle ground, okay? You've probably never used them as a primary source because you've always had a teacher explaining stuff and then using the textbook simply to set math problems for you. But that's not how textbooks are supposed to be used. They're supposed to be a great resource to learn things. So textbooks are fantastic. Then there's papers written by academics and stuff in the field, cutting edge information, assumes you've been doing this for 10 years. So it takes a long time to read a paper. It still takes me several hours to read a several page paper. If I'm going about 2 pages an hour, I'm doing pretty well through a good quality paper. I'm Googling stuff constantly to make sure I know what's going on. They are peer-reviewed generally, so I can't publish something without sending it to a few other experts in the field who read it and go, that's not correct, you need to fix that. Which is why they're deemed to be these holy grails of information, and they are generally very, very good. They are generally the best. That does not mean they are flawless, but they are generally very, very good. The duality here is the things up the top of this list are generally very easy to engage with, and the things down the bottom generally have very high authority. They've been peer reviewed, they've been assessed, but they're harder to engage with. You just walk into a new field and start reading papers, you're going to have a bad time. Okay, so generally we start up the top and we work our way down. Just as a quick disclaimer, because this is becoming more and more popular, things like open source journals are journals that are basically, they're pay to win journals. So I, as an academic, can submit a paper to it and get an expedited review process, they generally call it, where I pay $2,000 and they send it to the editor and only the editor, who is paid on how many papers they publish a year, and it gets in. Okay? There are pay to win journals, they masquerade as real journals, and they have crap in them. Just so you know. Just because you read it in a paper doesn't necessarily mean it's true. So let's do a quick example here. This was almost an N1500 project right back at the start. We never ended up running it for reasons that are probably going to end up becoming clear to you. So let's assume, though, this is our N1500 project and we're going to start on it. What do we do first? Well, the first place we go, try and sit a little bit lower. The first place we go to is Wikipedia. Okay, when we're trying to scope our problem and understand what we're talking about, you have $100 to design, construct, there's a comma missing there, design, construct, and test a trebuchet that fires a projectile with maximum momentum. Do you know what a trebuchet is? If not, even if so, I can't remember the meme. What was it? Something that could fire a 90 kilo projectile 300 meters or whatever. There was a meme about this like 2 years ago. Or if you play Age of Empires. We go to Wikipedia if we don't know what a trebuchet is, okay? They give us a picture of a trebuchet, great. They give us a plain English introduction, a type of catapult that uses long arm to throw a projectile. It was a common, powerful siege engine until the advent of gunpowder. Great, we know when they were used, what they were used for, and we've got a nice analogy. Cool. And if we go a little bit further down, I understand that text is very small. We are not going to read it all. It is basic design, though. It tells you what the components of them are and how they work to have a trebuchet. So this is a fantastic start. But that's not enough for me to go and build one with any high-level model. It's a really base-level model, right? Lots of assumptions. Now we're going to go to a more complex article that I just found these online, but it's a more complex article. So found a more complex article. Links to everything below in the description. So you can look at these articles. They're really quite long, and I'm cherry picking bits out of this to make my point. We get another picture. It's a more complex picture. It's a more complex model, right? And we get some more maths than we had before, modeling the arm and the acceleration of the projectile and stuff like that. But with this, I can start to do calculations. I can start to determine things like lengths, and angles and all sorts of different stuff, energy inputs, accelerations, so that I could start doing calculations, building a more complex model, and optimizing. It's getting harder. Glad I know that it's a catapult before I launch into any of this. And then we can go up another step, and this is a more complex article that I found on it, where people did a whole bunch of they actually modeled a whole bunch of trebuchets. So they made analytical models of trebuchets, and they played with all of the variables. So this is the kinematics. They put all of the accelerations and stuff, like they did all the math, they did all the modeling, and then they simulated a whole bunch of trebuchets with different variables in them, and then they could determine optimums. This is not the first article to read if you don't even know that a trebuchet is a catapult. This is a mess. This is hard for me to read, as in I don't think I even got through it. It was impossible for me to read. It was too difficult. So you don't want to start at the super developed end. It's too complicated. You want to build up towards this. This is incredibly important in the way that you do research. Because otherwise, this person could be spouting trash at you and you would have no idea. And people do this all the time. They overly complicate their explanations in order to make things seem, to make people believe them. So this is basically it was a really quick example of how we might go through a research process of something that we knew nothing about. How long does this research project realistically take? Well, It never ends. It never ends. The more you know, the better you are at problem solving in that field. And if you're going to stay in a field, you'll never stop doing research in it. But we got to put some limits on it. At some stage, we have to get to work. So in Eng 1500, you'll spend the total of hours to days. You'll probably spend 20 to 30 to 40 to 50 hours doing this, depending on how much you count your workshop time. You continue through your degree, you hit your final year project, you do a 12-month long project. You'll probably spend days to weeks scoping that out to begin with. And if you do a PhD after that, because you're, insane, you will spend months to sometimes over a year doing nothing but researching the literature that's already out there. And there are people who will get 12 months into their PhD, they have not done an experiment, they are still reviewing literature. I didn't do that. I started experiments way before that. But to each their own. Doing this allows you to determine how complex of a model you are going to build. It will allow you to make more complex models, or maybe decide you don't need to. And it will allow you to optimize problems rather than just solve them. Can we improve upon the things that are out there? I really love this quote by Newton. If I have seen further, it is by standing on the shoulders of giants. Marvelous people have come before you and done huge amounts of research, and they've spent enormous amounts of time documenting it in a way to make your life easier. That's our main job as researchers. Use that. Improve the human race by using the things that we have learned and leapfrogging beyond the things that we have done. This is what we want out of our engineers in the future and our scientists in the future, okay? I don't want you to have to rediscover all the stuff I struggled to discover. I want you to take that as assumed knowledge and then use your time to do the things I couldn't do. Okay? That's why we do research, so that we can be better than those who came before us, because we have more resources than those who came before us. All right, we're getting to the end. Analyzing data. This is like the second half of the research bit. Let's say you've been doing this. You've been out in the field, or you've been searching on the internet, and you've been grabbing data from left, right, and center. And you come across some data, and it looks like this. Two data sets, a red and a black, and most people would look at this and say they are quite well correlated. And you can do some maths and say, yeah, of course. Like, these clearly are showing something that is related. That is obvious. They have a correlation of 99.8. To give you some context, a 95% confidence interval is generally accepted in things like medicine. They will, if it's within 95% correlation or confidence interval, then it would be accepted to be true. And this is 99.8. So, you can't really expect to get a whole lot better than that, yeah? You can probably see where I'm going with this, but my point that I'm bringing us towards is correlation does not mean causation. Just because these two things are brilliantly correlated with each other doesn't mean they have anything to do with each other. They could be, and this is really suggesting that you should look into this, because they probably are, but just because two things are behaving the same way doesn't mean they are doing the same thing. So, your potential options when you see data like this that could be happening. A could cause B. Red could cause black to happen. That may be what you thought was going on. As the red one goes up, the black one goes up. The opposite could be true. As the black one goes up, the red one goes up. So it can... causation is generally one way, and it's often taught as it is explicitly one way, which is not true, but it's often one way. One thing correlates to another. The good example there is if I have a thermometer. As the temperature of the room goes up, the thermometer value goes up. But the value on the thermometer doesn't actually change the temperature in the room. I.e., if I break that thermometer and take some liquid out of it, the height of the thermometer goes down, but the room doesn't cool down as an association of that. So the causality only goes one way. You've got to make sure you've got that the correct way. But it's also entirely possible that it goes... Oh, well, actually, no. Okay. It is entirely possible it goes both ways. One causes one and one causes the other. Another thing that's possible is that something else happened, option C, and both things are a result of that. So that one's really common in media. Classic example. Overhead power lines cause cancer. there is a correlation between people living under overhead power lines and people getting cancer, but there is a common cause. Lower socioeconomic environments, so people without as much money, do have higher risks of cancer because they have less access to healthcare and they don't necessarily eat as well because it's hard. They also often live under power lines because it's cheaper. So there is an external cause that causes both of these things to happen, and then you perceive that they are related when they're not. Bidirectional causality is what we talked about, and A causes C and C causes B, a more convoluted loop. The final and most important one is there's absolutely no correlation, connection at all, and this is totally a coincidence. And obviously I cherry picked my data to make my point, but there is a website, again, link in the doobly-doo below, that will show you a whole bunch of these. And they're generally pretty morbid. That seems to be the best way to make these points for some reason, of weird correlations and of things that are clearly not related to anything. So, the most important takeaway when you're looking at this is, how well do you understand the models? All of the data that you've collected is based on models and assumptions. Can you put any physics to it? Can you put any science to it that says these things should be related to each other in this way? Or can you not? Is it just random data that you happen to have obtained? Because the statistics can get messed up really quickly, all right? So if you do this from just a statistical perspective, there's a whole bunch of things that are like, yeah, guaranteed, this is definitely a thing. And then you go, hold on, you're missing a piece of physics here. So cows are 300 times more likely to kill you than coyotes. Yeah, that's because we farm cows. We don't farm coyotes, right? So that doesn't tell me that a cow is necessarily 300 times more dangerous than a coyote if I meet one out in the bush. It's not 300 times more likely to kill me. I should be just as scared of the coyote, all right? So that's just an easy way where people can misinterpret data based on a true fact. Like, the fact's not wrong. Cows are 300 times more people may die from cows than coyotes, but it's a misinterpretation of the fact to say cows are more dangerous. Okay? Sweet. So that's one thing. And you want to be very careful with data that you obtain and how you interpret it. So this is another thing that gets around. Two people staring at the number, is it a 6 or is it a 9? And it leads to a series of things that basically say two opinions can be right at the same time. And generally, no, they can't in science. You might be looking at this based on the data that you have, and you may have formed this opinion. But once you find a contradictory opinion to yours, it's not your job to just stake your claim on your territory and say, nah, I'm right. It's your job to go and find more data, to go and see if you can find anything else around you that indicates whether this is a 6 or a 9. Which way does it go? Is their example here is like they need to back up and orientate themselves, see if there are other numbers to align with. Maybe there's a driveway or a building face that you can use. You can get more data to determine whether you're actually right or not, okay? And that is your job as an engineer. As you get partial data, you form opinions. You should challenge them either internally or get teammates to help you challenge them externally, and determine what you can prove versus what you simply believe. And then you can make decisions based on data instead of opinions. Now, you're not always going to be able to do this, and sometimes you're going to have to make an assumption because you just simply can't work this out, and your team's going to go, all right, we don't know, and we're calling it a 6, and we're going to document that assumption, and we're going to tell our client that assumption, and if they're unhappy with it, they can argue with it, but we're going to make that assumption. And so sometimes you have to do that. That's just the universe in which we live. But generally, we want to try and prove that we are right, okay? Because that which can be asserted without evidence can be dismissed without evidence. If you're just going to say, nah, I'm right because it makes me happy, it's meaningless, right? So, my way of doing this personally, and the way I do it in all the teams that I am in, is everybody assumes they are wrong at all times. The default assumption is everything you know is wrong. That is how I live my life. And we try and prove things correct from that point. And when somebody brings me something, I may emotionally like agree with them. They come to me, hey, is this a good idea? Hey, should I do this? Or I want to do this. This is my design. And I just take the total opposite point to them and just be like, well, I don't believe you. Prove this to me. I think that's wrong. I may personally think it's right, but I'm going to say, I think that's wrong. Can you prove it to me? Can you disprove this argument that I can put up? Now, I'm not doing that to be a prick to them. I'm doing that because that's how we make better designs, better products, is by putting them through that process and making sure we're not all sitting under a false assumption. Okay? It's really important. It is hard to do, requires a lot of trust between you and the person that you're doing it with to make sure they know you're not attacking them, you're attacking the idea, and you're doing it to make it stronger. It's difficult, but it is important. And it is a thing that you want to be careful with. At the end of that, you always go back and be like, cool, hey, that was really good. I think we did a lot better here. I'm on your side. It's very difficult to do with one entire problem. It's much better if you can break it up into little bits and you can test the bits independently. That will make it stronger. This is something where we like to prototype. So instead of designing an entire thing and going, this is my whole solution, oh no, I got this one little bit wrong and now everything is trash, we prototype, we make parts of it, we test those parts independently, and then we try to assemble them together. In week 4, we will talk a lot more about prototyping. Oh, also calibration is important. I see this happen in teams all the time in 1500. My idea is really good, and then they get into a pissing contest with somebody else, and you don't have anything to compare it to. Good compared to what? Acceptable versus good are two really important things for you to get. And again, we'll talk about that in prototyping. Okay, so just to kind of clarify a little bit of that, measuring and interpreting data, when you get it, there's a thing called confirmation bias. You will believe data that backs up the things that you already want to believe, more than data that contradicts yourself. They're called echo chambers. This was a huge deal with like media stuff, that it will keep showing you things on social media that are related to your searches, which reinforce things that you already believe and don't expose you to contradictory evidence. That is bad. You should go actively looking for information that doesn't agree with you, because that's important. And your clients certainly will. The better you understand a problem, the easier all of this becomes. It is hard at your level. I understand that. It takes time. You get better at it with time. You'll be fine. Okay. Really quickly, towards the end, as we do analyze this data, it's often good for us to constantly be checking our references and know when we should be referencing something. So basically, if somebody was to repeat your work, what would they need to know? Well, I read this thing and it was really useful. You should be referencing that thing. Okay? Give credit where credit is due. You can always, nobody's ever been upset by somebody who over-referenced. If something helped you, tell the world about it. Because A, great. Also, B, as an academic, my life is like literally based, as a researcher at least, on how many people credit my articles. That's like my number one KPI. So academics really want you to reference. Industry doesn't care so much, but academics, who are the people who are going to teach you for the next 4 years, really like it when you reference. Just because you have a reference doesn't mean that you are 100% true. References are good for supporting an argument. They don't necessarily prove it, okay? And if you've got one reference that supports you and I find one reference that contradicts you, you could be in a little bit of trouble, all right? So don't just assume, oh, it has a reference, it must be 100% true. Sometimes it is, but not always. Being said, you should question anything without reference. Again, doesn't mean it's not true. Just mean you should look at it with some healthy skepticism. Anybody who ever uses personal language to convince you of anything, which I'm fully aware I do all the time, again, be healthily skeptical of that. If I'm appealing to you emotionally, it may be because I don't have a great technical argument for the thing that I'm trying to say. Doesn't mean I don't, and it doesn't mean I'm wrong. Just if somebody's deliberately tugging on heartstrings, maybe they have ulterior motives. Don't know. Maybe. Get multiple sources. We've discussed this several times. Oh, this is a fun one. I always like to get people to go and Google go and tell me what is the strongest material? And without a shadow of a doubt, there's endless articles out there that constantly say spider silk, and it's just trash. Spider silk is not stronger than steel. Steel has got a range of strengths from like 200 megapascals to like 2.5 gigapascals. Hugely different variations of steel. No bit of spider silk is anywhere near the gigapascal range. And also, what does stronger mean? Because when they do the spider silk test, it's a single strand perfectly in tension. Well, that's not stronger means to me. I want to be able to put it in compression as well. Spider silk is useless in compression. So what this is a bad selection of data that leads people to believe things that are only true in unbelievably specific circumstances, and then they apply that knowledge to everything, and then they are very wrong most of the time. Cool. So yes, just because you can find me 30 or 40 references that say spider silk is stronger than steel, it doesn't mean that you are automatically correct. Having better references is generally more important than having more. Okay, let's finish it up. With that, we have covered today. Models are things that you will use in engineering. They will be wrong, and you will use them anyway, because despite the fact that they are wrong, they are still super useful. We now know that. We can now use them correctly to be super successful engineers. We've also learnt that units are also super useful to us. We know that now. We know why we have to do the little bit of extra bookkeeping when we work things out, because those units will help us make sure we are correct. And finally, we've gone over a bit of research skills, so now that you're a little bit better at processing data that you will get through independent research around your projects and then everything else you do from evermore. And I believe with that, oh no, I have one more slide. I have one more slide for week 2. I love this slide. You're 1% of an engineer. Okay, let's do some quick maths on a pretty dodgy model, but an engineering degree, 4 years full time, 2 semesters a year, 12 weeks per semester, which means to make an engineer, 4 years, 2 semesters, 12 weeks, 96 weeks of study at university is what it takes to make an engineer. You have gotten through week 1, which means you are 1/96th of the way through an engineering degree, which means you are just more than 1% of an engineer. I love this calculation. The main reason I love this calculation is because at some stage in your engineering career, it's probably going to get really hard to be here at university. And it's really great to be able to look back and go, hell yeah, I'm getting there. I'm making progress. I'm already 1% of the way there. It's just really cool, and you should be enormously proud of getting to the point that you have already gotten to. Remember to celebrate the little wins. It's super useful. So, well done. Thank you very much for sticking with me. Hopefully I'll see you all this week. But for now, we are done.